Okay. Hello, everybody. So we are, let's see, we are in our next unit, or not next unit, next lesson for Unit 2 here in derivative of trig functions. So we've learned power rule and we've learned product rule, quotient rule, all those rules. And now we're going to learn about how to take the derivative of each of the trig ratios. Okay. So there's a little warm up here that's practicing, I don't know, finding different things. So you can come back to that later. And you can try that on your own, but most of that is review. So let's jump into our first derivative. And we're going to find the derivative of sine using the graph. Okay. Now, let's do it this way. So we're going to find the derivative of sine of x using the graph. So let's graph. I'll try my best to draw this as good as I can. We are going to graph our sine function. Let's graph 2 cycles of it, okay, so we can clearly see this. And I'm going to graph it like I always do. So pi over 2, do pi right here, 3 pi over 2, and 2 pi. And let's go backwards as well. So let's do negative pi over 2. I'm trying to line this up as good as I can. I want to give myself plenty of space. Okay, and then let's see, just graphing our function. So 0 goes up 1, down negative 1. So like right here, 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 here. Really gonna make sure that curve looks good. All right, so there's my sine function. Now, let's take the derivative of this. So let's take the derivative of sine by graphing it. So this kind of goes back to one of those first few days we talked about with derivative functions. So what I'm going to do down here is below it, I'm going to do the same thing, but I'm going to graph. So I'm going to call this f prime or f of x. I'm going to graph f prime of x below, okay, based off of the slopes of my derivative function. Okay. All right. Why is it doing that? You see that? That's okay. Okie doke. So again, I'm going to say pi over 2 right here. I'm going to say pi and 3 pi over 2 and 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2. Man, I kind of don't want to be doing this in a video because I really want to see your reactions when you see what the derivative of sine is, right? So f of x is sine. Okay, let's do it this way. So let's remember how I said to graph your derivative function from the original graph. Start by finding where your slopes are 0. Those are like pretty much the guaranteed known like values. You're not guesstimating these. You actually know what these are. Okay. So like for right here, for instance, like what I'm saying is that f prime of pi over 2 is equal to 0, right? I mean, that's just where a maximum is on my sine curve. And I know that that's a horizontal tangent line. I'm going to put 0 right here. And there's the same thing over here, that the f prime of 3 pi over 2 is 0. F prime of negative pi over 2 is 0. And f prime of negative 3 pi over 2 is 0. I know those derivatives are that case. Okay. Now, the next one I'm going to kind of approximate is I'm going to look right here at the other interval. I'm going to look at 0 right here on my curve. 0 right here on my curve. The tangent line at this point right here. Okay. Um, I'm trying, okay, so I'm trying to draw it the best I can so you can kind of visualize what's going on right here. Right. For now, I want us to take my word on what this slope is going to be. If I did a rise over run here and figured out this slope, so right here, turns out that f prime of 0, the slope at that point is 1. There's actually a problem in the warm-up that's going to explain that, and I'm going to go over in detail why that is later. But for now, we know that right here, f prime of 0 is equal to 1. Right here. Now, it turns out it's the same thing right here at pi. If I were to compute that slope, f prime of pi is actually equal to -1. So it looks like right here. And the slope right here at 2 pi, all right, so f prime of 2 pi is actually equal to 1 again, just like at the origin. So it's like right here. At negative pi, it turns out the slope is actually -1 again. And at -2 pi, it turns out the slope is 1. Now, if I were to connect these dots, if I was to connect those dots, what am I left with here? What graph does that look like? Hopefully you're yelling it at the top of your lungs. This is the cosine of x. So the derivative of sine, and we just showed this by graphing each of these slopes, these tangent lines. If I were to graph the slopes and connect them, it turns out that the derivative of sine is cosine. Meaning, if I want to know the slope at any point on my sine graph, you can get that from your cosine graph. How cool is that? So we know that that sine, the derivative of sine, is actually cosine. Okay. Now, let's do that same logic here to figure out what the derivative of cosine is using its graph. Okay. Now, I'm actually going to pause the video, so I'm not taking away from the time of the video. I'm going to pause the video and go ahead and draw out the x and y axis, so I'm not wasting your time. So how about this? Abracadabra, alakaz, and voila, there you go. There's my graphs. Went ahead and drew those for you. So now we're going to find the derivative of cosine, all right, using the graph. Now, we already know that the derivative of sine is cosine. Let's see what relationship we have here. All right, I'm going to draw cosine. We know how to draw cosine. There is one cycle of my graph, and I'm just going to do one other cycle over here, just so we can really see it. Okay. And I encourage you to pause the video and try this on your own. But let's go ahead and graph the slopes of this. So I'm going to start with my slopes where I know they're equal to 0. Okay, that's at -2 pi, -pi, 0, pi, and 2 pi. So I'm going to plot those zeros right here. I'm going to do them green. There, 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 and there. And by the same argument as before, I know that the slopes right here in between the maxes and the mins, and again, we'll discuss more of this in warm-up, that those slopes are actually equal to 1 and -1. So 1 and -1. Here it's 1, so the slope is 1. Here the slope is -1. Okay? And if you were to connect, and all the slopes in between that are continuous, so all the values right here look like this if we were to connect the dots. So all I did was take f of x being cosine, and I just plotted the derivative values and connected the points. So this is f prime of x below here. What does this look like? Well, hopefully you're making the connection that since it starts off at 0 on the midline, it's a sine function, but it's not just sine of x. Notice how it starts by going to a minimum. So this means that it's negative sine of x. So the derivative of cosine is negative sine of x. All right, so keep track of this. We know that the derivative of sine is cosine. The derivative of cosine is negative sine of x. All right, let's keep going. All right, Now, I'm not going to do the same thing for the other 4 trig ratios where I graph it and sketch it out, all that stuff. We're going to do a little bit better than that. We're going to use the quotient rule to find the 4 derivatives of our other trig ratios. Okay, let's start with tan and secant. So the derivative of tan. And I said to use the quotient rule. The reason is because this is the same thing as saying the derivative of sine over cosine. That's what tan is, sine over cosine. So let's do the quotient rule. We're going to do low, which is cosine, d high, oops, let me erase that, sorry. Low, d high, and we know that the derivative of sine is cosine, minus high, which is sine of x, d low, and we know from before that the derivative of cosine is negative sine of x, all over low, which is cosine squared x. All right. Now, if I were to simplify this out, notice that we have on top, we have cosine squared plus sine squared. So cosine squared x plus sine squared x over cosine squared x. Okay. And that's what the derivative of tan is, but notice how it can simplify a little bit further. What is cosine squared plus sine squared? Well, hopefully you remember that's your Pythagorean identity. Okay, so that's going to be 1 over cosine squared x. And I think we can take it even a step further than that. 1 over cosine squared x is the same thing as secant squared x. So we just showed that the derivative of tan of x is secant squared x. So that's, again, something that you need to keep track of. Derivative of tan is secant squared, and we just showed why. Let's do the same thing for the derivative of secant. And we're going to do quotient rule again, because this is nothing more than the same thing as saying 1 over cosine of x. Okay? So, quotient rule. Low, d high, the derivative of 1 is 0, minus high, d low, and the derivative of cosine is negative sine of x, all over low. Okay. Now, on top, cosine times 0 goes away, and negative 1 times negative sine is positive sine. So what I'm left with is positive sine of x over cosine squared x. Now, sure, it's fine to leave it that way, but there is an identity for the derivative of secant of x. So we want to simplify it a little bit more. This is the same thing as sine of x over 1, or I'm sorry, over cosine of x times sine of x, or I'm sorry, I keep messing that up. I'm trying to split it apart if you can't tell. So sine times 1 over cosine. Do you see how all I did was just split it apart? Like if I multiply that across, sine of x over cosine squared x, right? And we know what each of these pieces equal, right? Sine over cosine is the same thing as tan of x, and 1 over cosine is the same thing as secant x. So that means that the derivative of secant is actually, I always write it secant first, secant x tan x. So there you go. Derivative of tan is secant squared. Derivative of secant is secant tangent. Okay, good. Oops, not there yet. I need to scroll down. Let's do the other two. So we got cosecant and cotangent. Okay. All right, cosecant first. Again, we're going to say that this is the same thing as taking the derivative of 1 over sine of x. Okay. So low will be sine of x. D high is 0 minus high, and then derivative of sine is cosine of x, all over sine squared x. So we're going to notice that the sine times 0 goes away, and we're left with negative cosine of x over sine squared x. So it's very similar to secant, But I don't want to write it that way. I want to write it as negative cosine of x over sine of x times 1 over sine of x. Now, this is the same thing as negative cotangent x times cosecant x. So I'm going to write that right here. I'm going to say this is negative cotangent x cosecant x. All right. Now we're going to do the same thing with cotangent of x. This is, again, using our quotient rule. We're going to say cosine of x over sine of x is what I'm taking the derivative of. So doing low d high minus high d low. Low d high, derivative of cosine is negative sine of x, minus high, and d low, the derivative of sine is cosine of x, all over low low. All right. Now simplify the top. That's going to end up being negative sine squared x minus cosine squared x all over sine squared x. Now, what you're probably realizing and seeing in the top here is that it looks like Pythagorean identity. But in order to do that, we have to take out that negative 1. So we got negative 1 sine squared x plus cosine squared x all over sine of x, sine squared x. And we know that this goes to 1, so we got, by the Pythagorean identity, so we got negative 1 times 1 over sine squared of x, which we know is nothing more than negative, what's 1 over sine squared? Cosecant squared x. So that being said, I know that this is equal to negative cosecant squared x. Okay, so mathematically and graphically, we just showed all 6 derivatives of the 6 trig ratios. And this chart here, I have it summarized. So all that we just did was proving these 6 derivatives. So really make sure you keep this chart available. All right, these are the derivatives of the trigonometric functions. You see sine and cosine we did graphically, and the bottom 4 we just showed doing the derivative rule. So please, please, please remember these. Let me just write this so you have it. I'm gonna do this. I'm gonna do this fancy little way here. I'm not gonna write it. I'm gonna type it. Aha! Just keep this in mind right here. Put an F. If trig function starts with C. Like I'll underline that. All right, stop underlining. So if a trig function starts with a C, then its derivative is negative. All right. If a trig function starts with C, then its derivative is negative. And that's just a little something to help you kind of remember that little piece of it, remembering which one's negative and positive. So what I'm saying is notice C, 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 negative, negative, negative. All those derivatives are negative. So that's just something to keep in mind there, a little trick to help you out. Another trick that kind of helps me memorize this, at least for sine and cosine, is I always draw this little chart, mostly in my mind, but I picture this chart in my mind. You know how like sine is like the y values for the unit circle and x is the cosine? So think of it this way. Here's positive cosine, negative cosine. Here's positive sine for y and negative sine. So I picture the unit circle this way. And taking the derivative of these functions is kind of like going clockwise. So the derivative of sine is cosine. The derivative of cosine is negative sine. If you take the derivative of negative sine, you probably guessed it, it's negative cosine. And if you take the derivative of negative cosine, you're actually back to sine. It's just a big old circle, right? Taking the derivative of sine, cosine. So I'm always picturing this circle. My math teacher in high school, she made it to where we had her we hold our hands up and we just kind of like go like a clock, counterclockwise. Or I'm sorry, going clockwise. I apologize. We go sine to cosine, cosine negative sine. And so you'd see people during a test just with their hands up in the air, waving them around, trying to remember this little mnemonic device or whatever. So that helps me, and hopefully that helps you. But that's how I always remember what the derivatives are. For the other ones, I just know that secant and cosecant has cosecant and secant in it. And remember that tan and secant are always together, and cotangent and cosecant are always together. So you see secant and tan, and cosecant and cotangent. There's that commonality between the two. So whatever you got to do to help you memorize these 6 things, do it. But it is very important that you do. Okay. All right, I'm at 21 minutes. I got through the main gist of the content. Maybe I can do a couple examples, and we'll save the rest for class. Okay. So yeah, I only got 3 more slides. I'll do this one example and then maybe cut it after this. All right. We know the derivatives of everything now. So here it says, differentiate, take the derivative of secant x over 1 plus tan x. All right. I got a quotient with a bunch of trig in it. So let's do the quotient rule. So in this particular example, y prime equals, all right, low d high. So low is 1 plus tan x, d high, all right, derivative of high, secant, is secant tangent, secant x tangent x. So that's low d high, minus high, and then d low. Derivative of 1 is 0, so that goes away. And the derivative of tangent is secant cubed, secant squared. I'm getting ahead of myself. X. All over low, or all over 1 plus tan x. So we did the quotient rule. Oh, squared. Sorry. Low, squared. Now, to simplify this, it's pretty simple. All you do is just circle the answer and we're done. Okay. If I ever ask you to just find the derivative, you can leave it unsimplified. I guess if you want to get crazy, you can make that secant cubed and FOIL this if you really want to, but it's okay to leave it this way. All right. All right. What else do I want to do? Kind of want to save those last 2 examples for class. I think that'll be good. I will do this example right here. I'll finish with this. Notice how these 2 problems are the same exact problems. Originally, the reason why is because I was going to show you 2 different ways. The first way, doing the product rule, practicing the product rule. And the second way was to then just distribute and show you that. But upon doing this, I realized that if I were to distribute, I'd just end up doing the product rule twice. Do you see that? If I distribute this, this is going to be the cosecant x of 3 x negative 2, and then plus cosecant x times 7x. But then you notice if I want to take the derivative of this quantity and the derivative of this quantity, they are again 2 products. And I'd have to do product rule twice. That makes doing this method completely unreasonable. So distributing doesn't always make it a little bit simplified. That's only if they're all polynomials. So in this case, doing the product rule is probably the most simplified version of it. So I wouldn't distribute. Again, that's just going to cause you to do the product rule double time. Let's do it right here. All right, product rule. So derivative of the first, derivative of cosecant, remember, is negative, because it's a c, negative cosecant x cotangent x. Just try to remember that. So derivative of the first, keep the second the same, plus keep the first the same, And derivative of the second, the derivative of 3x negative 2 is going to be negative 6x negative 3, and then plus 7. Okay. Now, in order to simplify this, again, real simple, all you're going to do is just box it, and you're done. Don't simplify if I'm asking you to just find the derivative. You can leave it that way. I promise it's okay. Now, if you were to do the same thing over here, setting it up this way, it's going to be a little bit longer of an answer, and it may not look 100% just like this, but it's going to be a equivalent form. And it's just a little extra work to do it that way. So leave it off of this. All right, I'm at 25 minutes. I'm going to go ahead and end it here. I'll do the last 2 examples tomorrow. You're welcome to go ahead and try them on your own and check your work so you can be ahead of the game. That is completely up to you. So, y'all have a great day.